Hi, this is Homework 1, Part B. Here, I will be deriving the material and energy balance for this CSTR. As you can see here, there is a chilled jacket around it. This is an exothermic reaction, and we are going from A to B. So to start, I want to simplify our system here. So we have a CSTR, which means that our solution in the tank is going to be continuously mixed. Therefore, our Ca out is going to be Ca, and then as well as our Q in and Q out are going to be equal because we've been at some steady state at the same conditions. So we can get rid of the Q in and Q out and just make it Q. Alright, so now with our material balance, we need to start with our flow in to the tank multiplied by the concentration in, and then that will be subtracted by the flow out of the tank multiplied by the concentration leaving the tank. And we can simplify that to just the flow rate times the concentration in minus the concentration leaving the tank. So now we need to include in our material balance the rate of reaction, and we know that the rate of reaction R is equal to K, the rate constant, times the concentration Ca. And the rate of reaction R is per volume, so when we include this into our material balance, we will need to multiply by volume as well. So next we need to subtract our rate of reaction, K, Ca. However, we need to again multiply by our volume. And then everything we have here is going to be equal to our change in concentration in our tank with respect to time. So we can denote that as our differential of concentration over dt, and then we will again need to multiply that by our volume to account for the entity of our system. So now that we have this expression here, we can go ahead and do some more simplifying. So we want to be left with just the change in concentration over time. So doing so, we can just divide by volume, and that gives us the differential of our concentration over time is equal to Q over V, so our volumetric flow rate over the volume, and then multiplied by the differences in our concentration subtracted by our rate of reaction. So here is our material balance. Next we will move into our energy balance. Okay, so for our energy balance, our expression is going to be a function of our density, our temperature, the specific heat capacity, as well as the volume. And this is all going to be evaluated as the differential with respect to time. And then we can start the right-hand side of our energy balance by taking the flow rate in of our tank and then multiplying it by our density, and that is the mass per volume. And then we will be multiplying it by specific heat capacity of our material, and then we will be multiplying the specific heat capacity by the temperature gradient of our system. So we can write that as T in minus our final temperature. So for here we have our flow rate times our density times the specific heat capacity multiplied by the temperature gradient, and then here we are going to want to add the heat of reaction, so that is the amount of heat generated from the exothermic reaction. So we write that as H reaction, and then that is going to be multiplied by, again, our rate of reaction, so that is kCa, and then that is per volume, so we will need to multiply that by volume as well. Okay. Okay, so next we need to take into account the coefficient of heat transfer, U. So next on our right hand side, we need to subtract the amount of heat that is lost. So that is going to be subtracting the heat transfer coefficient, U, multiplied by the area at which the heat transfer is occurring. So we have minus U times A for our area, and then this is going to be multiplied by the original temperature of our chilling, and then subtracted by the outlet temperature. So we have Tc minus T. All right. So here's our expression. I'm going to erase up here so I have some room. I have a bit of a glare at the bottom. All right, continuing with simplifying this expression here, we are going to want to get rid of everything that is on the left-hand side that is in our parentheses, and we want to be just remaining with the differential of our temperature with respect to time for this exothermic CSTR. So doing so can give us the differential of our temperature with respect to time is going to be equal to, so here we have rho cancels, we have temperature, the specific heat capacity, and then so we'll have our flow rate over our volume multiplied by the temperature in minus our outlet temperature, and then we'll be adding the heat generated from the reaction multiplied by the rate of reaction, and then this term will be divided by our density and then our specific heat capacity, C. And then lastly, we will be subtracting this last term here, the heat transfer coefficient multiplied by the area, so UA, and that is multiplied by the temperature gradient of our chilled water, and then this will all be divided by our density times the specific heat capacity times the volume. All right, so here is our second equation that we have derived for our energy balance of this system. Now we will move into Google Colaboratory and implement these equations and plug in some real numbers in order to see how this simulation works. Thank you.
Here we will be inputting our derived material and energy balance for the CSTR for Part B into Google Colaboratory. So here, table 2.3, we are given some nominal operating conditions for the CSTR. So we can go ahead and enter this into Google Colab and run the simulation. So first we need to import our libraries. Import numpy as np from plotly.subplots, import make subplots, and then from scipy.integrate, import solve IVP. All right, these in, we can go ahead and enter our nominal operating conditions. So we can say Q is equal to 100 liters per minute. C initial concentration is going to be equal to 1 mole per liter. Our initial temperature is equal to 350 Kelvin. Volume is equal to 100 liters. Rho, or density, is equal to 1,000, the units of grams per liter. Our specific heat capacity, I'm going to call that CP just for the code, is equal to 0.239, and that is joules per gram Kelvin. And then our heat of reaction value here is given to us negated, so we can go ahead and just define our heat of reaction variable as the negative heat of reaction. And then that is equal to 5 e to the fourth, and that is joules per mole. Next, we have our ER value, and that is equal to 8750 Kelvin. We have our K naught is equal to 7.2 E N. UA. UA is our heat transfer coefficient multiplied by the area of heat transfer is equal to 5e to the fourth units of joules per minute Kelvin. Our T C naught is equal to 300 Kelvin. And then Ca naught is equal to 0.5 mole per liter. Liter. And then lastly, we have our T naught is equal to 350 Kelvin. U C A I T I V rho conditions. We want to go ahead and start defining our function in which we are going to solve using the solve IVP function. So we want to define side of a function. And again, our independent variable is time. And then we are following it by our dependent variables here. And for this instance, we want to use a vector. And that is because we have more than one. We are trying to look at the concentration and temperature profiles. So on our next line, we can define vec, or we can define Ca temperature is equal to our vec. Our vector unpacked into our concentration and temperature. we now need to include the new coolant temperature value for TC, and that is going to be at 305 Kelvin at T equals 0. So we can denote that as TC is equal to 305. And again, that is Kelvin. Okay. All right, so now we can return the right-hand side of our function from our previous derivations. Side of our functions are going to be, and I'm just bringing this here so I can have it as a visual aid for these equations. So we need to return our concentration differential equation first. So the right-hand side is going to be equal to Q over V, and then that is going to be multiplied by CA CAN minus CA minus K times CA. And for our second, the right-hand side is equal to Q over V times T N minus T. That is going to be plus. So this value is already our negative heat of reaction. So we can just go neg HR times our K times CA. And that would be divided by rho times our heat capacity. And then on, we are subtracting our UA value, and then we'll be dividing that by rho times our volume times our specific heat capacity. And then this is going to be multiplied by our T minus TC. CN EIN. All right. So you notice here that we do not have a defined value of our K yet. However, we know that due to our rate of reaction, K is equal to K naught times E to the negative value of the activation energy over the gas constant times temperature. So let's go ahead and define that in here. K is equal to K naught times NP dot EXP ER shift enter. Turned the right hand sides of both of our differential equations for the concentration and temperature of this exothermic reaction in the CSTR. We now want to use the solve IVP function in order to get values and then eventually plot and analyze to see how this system performs under the simulation. So to start, we can define our solution as the result is equal to solve IVP, and then our function here is going to be the right hand side. The time span, we can go from 0 to t end. We'll need to define a t end. Initial guesses will have CA naught and then T naught. And then we need to make sure that we keep that in the same order as our vector so that the orders of our arrays and lists stay the same. So after our initial guesses, we want to move into our method, and that is going to be equal to redow. And then lastly, we would like to make our dense output equal to true. Define t end. Enter. All right, let's check it out. So the solver successfully reached the end of the integration interval. We have some times and y values. See, it's double list. So now we want to go ahead and plot these. First, we need to define some of our x values, and we can do that by creating a t-plot is equal to np.linspace 0 to tn to 200, just random numbers. So now that we have created our x values, we now want to go ahead and we want to input these values into our function in order to calculate our y values for our respected concentration and temperatures. So doing so, we can say our concentration and temperature is equal to our res dot our solution, and that is going to be evaluated at these values for our t-plot that we have created. So now we can go ahead and create our subplots now that we have x and y values. So we have fig is equal to make subplots, and since we'll have two plots that we want to have here, we can have rows equal to 1 and then columns equal to 2. Right. Fig dot add scatter x is equal to t-plot. Our y is equal to, well, let's go ahead and do our concentration first. And since this is our first plot, we can assign this in the first position. And then lastly, we want to give it a name. And this is our concentration profile. Okay. All right, now let's repeat that for our temperature. So we have fig dot add I can't see. Y is equal to T, rho name equal to temperature profile. Okay. I think this should update our layout. Let's go fig update layout. Width is equal to 800. Height is equal to 600. Okay. Oh, that's what we have our time steps going too long. Let's make this 10. All right. So here is our concentration profile as well as our temperature profile for the exothermic reaction being performed in the CSTR. Thank you.